The next talk by Andreas Klumper.
Yes.
And he'll be talking about open XXX spin-1 half quantum chain.
Right. Thank you. Yeah. So this is a talk on joint work with a couple of collaborators. I will mention on the next transparency, but okay. But before I start this talk, I would like to express that Professor Baxter, Rodney Baxter, meant a lot to me scientifically and personally. Scientifically, I want to say that I learned everything about integrability from his book and his papers. And in particular, about the star triangle equation as a sufficient condition for commutativity of transfer matrices, but also other methods which go well beyond just beta ansatz in the condensed matter framework. And as a result of this, so to say, teaching, I realized that I almost always prefer alternative methods to the beta ansatz, so like inversion relations. These are useful for calculating partition functions in the thermodynamic limit. If you're interested in finite size corrections, CFT data, you have to find the analogs for finite size. These are usually given by fusion relations and derived relations. Here the dots indicate TQ relations that are obtained, let's say, by non-beta ansatz calculations, and also the TQ relation. When you look at Baxter's book on the solution of the 8-vertex model, he derives TQ relations without beta ansatz, and he solves TQ relations without referring to or using density functions for the roots. Maybe less known is that he belongs to those who used Knizhnik-Zamolodchikov relations or equations for correlation functions very early. Maybe this Knizhnik-Zamolodchikov is a misnomer. Maybe one should call these equations Jimomiva equations or something like that. Anyway, Knizhnik-Zamolodchikov equations are differential equations in CFT, and these equations here are functional equations for correlation functions, and Professor Baxter used it, I think, after his retirement to calculate the one-point function of the current Potts model. Well, I do not ignore beta ansatz, but when I resort to it, I try to avoid working with root density functions. So outline of my talk is I'm heading to the spin-1 half Heisenberg chain with non-parallel boundary fields. And for calculating, let's say, the first thing to calculate is the ground state energy. And for that, I try to apply functional equations for the transfer matrices, like the T and Y systems I already mentioned. And from those one can derive nonlinear integral equations, which are good for extracting finite size data. And in Baxter's book, in his papers, you find such relations for the 2D Ising model, for the hard hexagon model, critical hard squares. Well, of course, he studied the RSOS models, but I think Paul Pierce and I were those who generalize these relations to all RSOS models of A-type. Although the T and Y systems are rather reliable, they do not solve the problem I'm heading at. And we instead use some kind of TQ relation for finding finite nonlinear integral equations. Well, this work is joint work with Holger Frahm, Dennis Wagner, and Xin Zhang. And here it comes. So inversion identities. For the 2D Ising model in zero magnetic field, the transfer matrix, and Tony Goodman already talked about this. The transfer matrix satisfies equations like transfer matrix at some spectral parameter V minus I times transfer matrix at V plus I is equal to something. not terribly complicated, actually a known function times the identity operator. And then, of course, you can take this equation, and Tony Goodman already explains that. I mean, you can take the logarithm and maybe then the Fourier transform, and then you express the logarithm of t in terms of the function f. So actually, you get the logarithm of the maximal eigenvalue of the transform matrix as a convolution integral of some kernel called S with a logarithm of this function f. So in short, log t max is equal to S star log f, and the kernel is this 1 over hyperbolic cosine. And for the excitations, there appear additional terms on the right-hand side. In the hard hexagon model case, I'm presenting here a simplified version of the equations. After suitable normalization of the transform matrix, we have some functional equation like before, t times t with differently shifted spectral parameters is something like identity plus something unknown, but it's the same object that appeared on the left-hand side. So you cannot really, this doesn't lead to an explicit expression for the eigenvalues of the transform matrix T, but it leads to an integral equation. So if you apply the same techniques as before, then you find that the logarithm of T is a convolution integral of the same kernel S with logarithm of 1 plus T. And then the appearance of these additional terms is L times log hyperbolic tangent. That's due to, here I dropped somehow normalization factors. So this is not an explicit expression, but you can solve it numerically, for instance, or maybe in certain limits by other means. So this is the first part, or these are the first steps of the full story of fusion and use of T and Y systems. For the SU2, possibly Q-deformed SOS models, here we are dealing with a series of transform matrices with index J. For J equal 1, we are dealing with a transform matrix with spin-1 half in the auxiliary space, and for larger values of J in the auxiliary space of the transform matrix, we have higher dimensional representation, but in the physical space, I mean, they live in the same physical space. They're mutually commuting, and they satisfy these relations for all indices J. So T sub J multiplied with T sub J, and spectral parameters shifted by plus minus I is identical to the identity plus products of T times T with shifted indices up and down, and no shift in the argument. And this is a general picture, at least for these SU2 systems. And one from these relations, one derives, called T system, one derives a Y system, and the Y system reads like that. Y times Y is equal to 1 plus Y times 1 plus Y, where the Y is just an abbreviation of the product of the T's. I'm going quickly through this because I just want to flash the main ideas, and in the end, these equations, although they are satisfied in many systems, do not help us solve the problem. I will explain. Generalizations to higher rank are due to Kunibak, Nakanishi, and Suzuki, and for higher rank, Kirchberg et al. Pointed out the relation to discrete Hirota equations and formulated Backlund flows. And derive beta ansatz equations from these T and Y systems. Okay, for the general case, we would proceed like that. We apply similar technology that I described before, and from the multiplicative functional equations, we get integral equations where no shifts of the arguments show up. Logarithm of y1 is equal to a bulk term, L times the log of hyperbolic tangent plus this convolution S star with log of 1 plus y2. So we have to know y2. When trying to calculate y2, you use the second line for j equal to 2, and then you see you are forced to study not only the y sub 1, but also y sub 3, and so on. It's an infinite hierarchy. For the Q-deformed RSOS models, this hierarchy truncates naturally at a certain level, and you're dealing with a finite set of integral equations. And once having the solution to these equations analytically or numerically, you remember the definition of the y functions. T1 times T1 is equal to 1 plus y1, and then you transform this functional equation in the same manner as before, and you find that log of T1 is practically the convolution integral with log of 1 plus y1. That's, you know, that from the set of the many nonlinear integral equations for y sub j, and you only need y sub 1. You can forget about all other y's. And then after doing this integral, you have the eigenvalue, let's say the leading eigenvalue of transform matrix T1, which is a physical transform matrix. And you can evaluate these integral equations and the integral expression for the eigenvalue of T1 for practically any size L, large or small. And yeah, the integral kernel is exponential asymptotics. And if you're interested in conformal data, the 1 over n, or here I should say 1 over L corrections, you don't need to do numerics. You apply the dialog trick and you get the central charge. By the way, in the course of my talk, I frequently change from L to N. So system size could be L, the length, or N, the number of sides. So don't be confused. Okay, I'm interested here in the spin-1 half XXX chain. For the periodic boundary case, we have a couple of methods. For instance, we apply this fusion technique to the transfer matrix of the 6 vertex model. The transfer matrix of the 6 vertex model generates all conserved quantities or charges, and the first one is a Hamiltonian and other things. But for the technique of calculating eigenvalues by the t and y systems, or by these functional equations, as we introduce not only the t, which is t1, we introduce t2, t3, etc. And then we derive this set of these nonlinear integral equations. They look practically the same as before. So in the first line appears the system size, now n, times the logarithm of the hyperbolic tangent. And in the next line, this driving term or source term is just 0. And that's why one can use these equations. Of course, numerically, infinitely many nonlinear integral equations are not really fun, but in principle, it's possible to do approximate calculations. By the way, the magnetization, as we know, some of the sigma z commutes with the Hamiltonian h and with all the other conserved quantities. Now we are interested in non-periodic boundary conditions. So here, sigma sub n plus 1 is identical to sigma sub 1. And we want to open the chain and introduce, so here we look at the same bulk interaction, and we introduce boundary fields. Due to the symmetry, SU2 symmetry of the system, we can always assume that on the first side, the field, vector h1 is just pointing into z direction. And on the last side, n, there is a z component and a transversal component which is just pointing into x direction. Yeah, so this is the most general form of the open boundary case of the spin-1 half Heisenberg chain with arbitrary fields. Later, these boundary fields h1z and hnz here is reciprocals is parameters p and q, and the ratio of the transversal part to the longitudinal part of the field on side n is called psi. Non-zero psi is a problem. We have the Baxter equation, reflection matrix equation, I mean, the Plianin relation satisfied, and the Hamiltonian is integral. We have again a family of commuting transform matrices, and we find the Hamiltonian as the first logarithmic derivative of the transform matrix, and the higher conserved charges via higher derivatives of log of t for any p and q. So everything looks pretty integrable, but as magnetization doesn't commute with h and these qn's for psi non-zero. Still, we have the same t system and y system as the functional equations in multiplicative form, but when you then transform them into nonlinear integral equations, you not only find these convolution-like integrals, but you find driving terms, because, I mean, for all levels, even for the ground state, and in all of these equations, you have non-zero contributions, because when you derive from the multiplicative functional equations, the integral equations, you have to take a logarithm of both sides, and in case that the logarithm of, let's say, these y functions have zeros in the physical strip, counter terms appear. And for the periodic case, nothing like that happens for the second line and third line, but for the case with non-parallel boundary conditions, you have a lot of dirt. That has been investigated by Fran and collaborators, and they never got happy with this. So we need something else. And before I tell what we use, this problem has been studied by many people: Nepometsky, Fram, Grelek-Seel, Nicoli, Faldella, Kitanin, Meillet, Nicoli, Kitanin, Terrasse, and a famous set of equations in inhomogeneous TQ equations were derived by Cao, Yang, Qi, and Wang. Later, so to say, rigorously proved by the method of separation of variables by Meillet and company. Other people worked on the problem: Billiard, Mentor, Compe, Avant, Billiard. Okay, you read it. And for the parallel field case, there's a paper by Professor Baxter and others, usually referred to as a paper written by everybody here in Canberra. So the paper had been cited already, and it was written in 1987. Okay, so what are the alternative methods? Back to TQ relations. I mean, some people would have said, why not directly? I mean, TQ you get from the beta ansatz, and this is proven, etc. Anyway, still we do, for the periodic boundary case, different things with it. So the TQ relation is transform matrix times this, it's a polynomial in the isotopic case. Q of V is equal to some simple function, actually the argument to the power L, so the system size times Q at a shifted argument plus another phi of, so a simple function at argument V plus I times Q of V minus 2I. And traditionally, people would look at the distribution of the zeros of Q of V. For the ground state, these zeros are distributed on the real axis, and then people introduce density functions for that. We avoid that. We use data of the Q function, but not on the real axis, but away from the real axis. And because the polynomial Q of V is an analytic function, I mean, all data on any line, I mean, determine the data on all other lines. So we look at the ratio of the first term on the right-hand side to the second term, and the other ratio, call these functions A and A bar. So down here, A and A bar are defined. You see, we mostly use the function A of V for real argument of V, but there's a shift, and that means we evaluate the Q function away from the real axis. And these so defined functions satisfy a set of nonlinear integral equations, which is written down here. A appears on the left and the right-hand side as log of A and as log of 1 plus A. And the complex conjugate appears on the left-hand side as log of A bar, and also on the right-hand side as log of 1 plus A bar. The kernel here, K or kappa, and kappa sub n minus and kappa sub plus is given here by a Fourier integral. One can write it down explicitly in terms of the gamma functions, but this is never used in our calculations. Yeah, and these are two nonlinear integral equations, and so to say, much better than infinitely many. Once these equations are solved for A and A bar, for some system size L, one inserts the solution into this integral here, the S prime, S prime and log of 1 plus A and log of 1 plus A bar carries the same argument V. I just dropped it for compactness. So that gives, let's say, the ground state energy for the periodic boundary case. And here are plots of the functions for different sizes. System size 10 to the 3, 10 to the 6, 10 to the 9. Actually, these data have been derived. So dash dotted line, black is the real part of log A. Capital A is a shorthand for 1 plus little a. So so the dash dotted line is for size 10 to the 3, the dashed line for 10 to the 6, and the solid line for 10 to the 9, and one can continue this. And what you see is that these curves look all the same. They just move out to plus infinity, minus infinity at a speed of log n. And this data have been derived just by programming everything and then letting the program run. And after a minute or so, the data is there and without human interference. So it's just a pleasure to calculate these functions. It's not such a pleasure to deal with a non-periodic case. The inhomogeneous TQ relation was derived by Cao Yang Shi Wang in 2013, and they use a particular parameterization which I find inconvenient. So we rotate the spectral parameter by 90 degrees on the complex plane and shift it, and then the TQ relation is written here. Look at the left-hand side, the little t of x is just the transfer matrix in the new parameter. On the right-hand side, you see a sum of 3 terms instead of 2 terms. And the phi 1, phi 2, phi 3 are, again, simple functions like powers of the argument, power to the n, and a few linear factors. The unknown functions are Q1 and Q2. Q1 and Q2 are not completely independent. Q2 of x is identical to Q1 of minus x. But still we need to find the zeros of these Q functions. And well, this TQ relation is called inhomogeneous because here we have a ratio in the first term, and the third term we also have a ratio, but in the second term we have a product in the denominator. So if you scale the Q's by some factor, it destroys this relation. We found out, we means Fram, Wagner, and Zhang, and myself, that the following combination of auxiliary functions are useful for some reason. I mean, it's difficult to understand it in a few minutes. So if you take these 3 terms that appear on the right-hand side of the transfer matrix, and you take the last 2 functions, sum them up, and divide by the first function, you get little a bar. I mean, it's a similar expression C, yet another one, and when you add ones to these A and A bar and C, then you see that these objects, these functions factorize, and they give the transfer matrix eigenvalue. And so, I mean, factors that appeared already on the left-hand side. So this is nice about them. And then you can derive nonlinear integral equations for all 3 functions. I mean, A and A bar by themselves do not satisfy closed systems of equations, but the 3 do. Before writing down these integral equations, I want to show to you the graphs of these functions for system size 10 to the 3 and some boundary parameters. Actually, we use P and Q negatives. That means the boundary fields point into the same direction. So, which is important in opposite directions, we would have different appearance of these graphs. Anyway, when you look at the real part of log of capital A means 1 plus a, little a, then you see it looks a bit like before. So in some inner part between plus and minus log n, that function is 0. It applies also to the imaginary part. And then at this value x0 of the order log n, the functions become non-zero. And then interestingly, at some other value, somewhat larger, the imaginary part does not go to 0 as before in the periodic case, but now it winds up to 2 pi. And when looking at these functions, you understand that the integral equations, if they exist, must be looking more complicated. And here they are. So on the left-hand side, log little a bar, log little c, and on the right-hand side appear convolution integrals. Now we have a kernel matrix, 3 times 3. The same kernels that as before appear, these kappas, but then there are additional functions in the kernel which are rather long-ranged. These are Cauchy type kernels, slowly algebraically decaying. And in order that these, and here there are different ways to write down these equations. I prefer the way to subtract logs of rational functions to have the input data into the kernel of the type without any winding. And these parameters x plus r, xr plus minus, xl plus minus r look, so they have as real part the position x1 that I pointed out before, and these parameters have also some imaginary parts. Anyway, these terms also appear in the driving term. I don't want to talk too much about this, and I would love not to show to you the driving terms, but here you see, before we had just system size times log of hyperbolic tangent, and that's it. But here there come logarithms of gamma functions, logarithms of rational functions, and also for the third function there comes a logarithm of ratio of some function. And what you directly see is that this additive scaling that was done in the conformal limit to derive the 1 over n corrections for the periodic case is meaningless here. It simplifies the driving terms number 1 and 2, but then in case 3, it leads to nonsense. So now let's look again at graphs for larger system sizes. For system size 10 to the 6 and 10 to the 9. There, the functions look completely different. Before, the winding from 0 to 2 pi appeared at a value larger than log n. Now it's the opposite. The winding happens at much smaller arguments. And also in this case, now the function c is no longer flat, but develops some structure. And you wonder what happens in the true thermodynamic limit. Now, what we would love to do is to derive 1 over n corrections. For that, we used to use the additive scaling limit, because the function, the profile of the function log a moves out at a logarithmic n speed, and that gave us access to 1 over n corrections in the periodic case. But when you take these 3 nonlinear integral equations for the non-periodic boundary case, you get nonsense. So as a first step, Xin Zhang and I, we look at a multiplicative scaling. So we look at the functions and don't follow these profiles at a speed of log n further out. We just zoom out. So we look at, we introduce so to say, a new scale, x0. So everything, all distances are measured in multiples of x0, and then the integral equations simplify a lot. So for instance, the kappa integral kernels simplify to delta functions, but of course the Cauchy-like kernels, they remain. And we have now much simpler equations, but they are still of convolution type. And here are pictures of these functions in this multiplicative scaling limit for different values of psi, 0.1, 0.5. So these functions, so in the multiplicative scaling limit, do not depend on any boundary fields any longer. They only depend on the angle between the boundary fields. And you see, instead of having a function c that has a 0 of second order for spectral parameter 0, and we have now a pole of second order. And and at x0, or I should say at argument 1, alias x0, the function c goes through 0, and it's otherwise continuous. But the function log a, the real part and the imaginary part, they jump at 1, alias x0. And when taking these data and then applying some analysis, we understand how to do the additive scaling limit, and we get the following result. Well, the dialog trick is applicable, and we get for the finite size data. So we look at the ground state energy, subtract the bulk energy, the surface energy. The surface energy is calculated explicitly just in passing, and then we get minus pi velocity divided by 24 times n, not times 1, but times 1 minus 6 times 1 minus some parameter phi over pi squared. This phi, so to say, angle phi, is a function of the angle between the boundary fields. It's a function of psi, and it looks as if this function is simply an identity. So this phi is the angle between, it's not just a function, but it's identical to the angle between the boundary fields. In any case, what we found is that these finite size terms depend on this angle, that do not drop out. When you evaluate that, let's say for very small values of phi, you realize in the brackets you have a negative number, so the total finite size term is positive. For vanishing boundary fields, you just get a negative term, namely minus pi v over 24n times 1. But that can be understood. So why do we get a qualitatively different result, and why is it non-continuous? The system is interferomagnetic. The number of sides is even. So the boundary spins 1 and n want to point into opposite directions. But here we have applied boundary fields which have longitudinal components in the same direction. So this is qualitatively violating the natural tendency of the system. So that's the end of my talk. I presented 3 nonlinear integral equations for the Heisenberg-Chandler broken conservation of magnetization. Potentially much more useful than direct beta ansatz methods. The direct iterative treatment of the nonlinear integral equation suffers from instabilities, in particular for large values of psi and intermediate sizes. So for small sizes and for large sizes, we can do the calculation, but it's difficult to follow everything. Okay, so there are some conjectures left in this treatment, but certainly the finite size data depend on the orientation of the boundary fields. To do checks, anisotropy XXX chain with open boundary fields, and that's it. Thank you very much for your interest.
We have some time for questions.
What was the x0 in the multiplicative scaling?
Yeah, this was, so the precise definition is x0 is the 0 of function level c. But this is always of the order 2 over pi times log n, log system size. So in the multiplicative scaling limit, you can identify x0 directly with 2 over pi times log n. Yeah. And yeah, so So what we found confusing in this entire treatment is that for small system sizes, the functions look completely different from this any reasonable scaling limit. Absolutely different, yeah. And that took us years.
Any more questions?
Could you say a little more about the conjectured scaling limit?
What the conjecture is, the calculation of the conjectural scaling limit works well. Okay, so this year, the conjectural scaling, bless you, whatever. So when we do the scaling limit, this year, when we look at these functions, then they have to satisfy these equations. So this is, of course, only meaningful if the physics or the mathematics wants it. But if you take those equations in this, I mean, from the point of view of a pure mathematician, it's a conjectured scaling limit. If you take these equations, those can be solved easily on the computer. So without any human interference, I write the code, I hit the return button, I wait half a minute, the data is there. So that is, and it looks like this. So the C function is continuous. Log A in this multiplicative scaling limit jumps, and the additive scaling limit would inflate or zoom in at this point. Then there you do the Sommerfeld expansion, yeah? And then you see all the contributions by the function C can be replaced by a constant, and then you do the same calculation you did for the periodic as you did for the periodic case, and this dialog trick, and then we get this here.
Thanks. There is a question from Jan de Geer online, actually. Does the nonlinear integral equation method extend to the ASAP case and higher rank cases?
ASAP case and higher rank. Well, for doing these stochastic systems, I looked at this approach, but I think somehow there's a paper by Jan de Geer and Fabian Essler. They use a different method, yeah, and then I gave up. I thought I'd do different things, but I studied this problem. Sorry, and maybe I should look at it again.
Okay, so let's thank the speaker again.